Today's lesson is going to look at Cartesian equations of lines. Yesterday we looked at lines in R2. We developed an idea of how to write the equation for a vector in R2 using vector form and parametric form. Today we're going to look at a third form. The third form, called Cartesian or sometimes scalar, is something we know of as standard form from grade 9 math when we learned about the equation of a line. So like we had y equals mx plus b, and we turned that into a vector equation. Today we're going to turn vectors or parametrics into Cartesian equations. So the form that we're looking at is this ax plus by plus c equals 0. So a, b, and c are just coefficients. So for example, you could have 2x plus 3y minus 4 is 0. Okay. The three forms we're going to use, vector, parametric, Cartesian, totally interchangeable. You need to be able to work from one or the other or back and forth between them. Okay, so we'll start with something simple. So we'll go back to grade 9 math almost, if you will. So here's a line, y equals 1/4 x plus 2, so mx plus b form. From yesterday, can you write this in vector and parametric form? Well, we know that we need a point and a direction, and we can turn that into a vector equation very easily. And we have a point. And the point that we know for sure is the y-intercept, so 0 and 2. And in vector form, we need a direction, and our direction is x and y, or 4 and 1. Here's your vector format. Our parametric form, we said yesterday, is what's the x part made up of, what's the y part made up of. So x is 0 plus 4t, or if you want to, just 4t. And y would be 2 plus t. Okay, our new idea today, Cartesian form. Let's start with the old-fashioned way of doing this, first of all. Cartesian form, remember our order is ax, by, c is 0. Well, the easiest way of doing that to this equation is start off by changing our order. We put our x term first, then the y term. So we're going to bring the y over to this side. It'd be a minus y plus 2. And we have nothing left on the other side. Now, technically, it's actually over here, but it means the same thing as if we put it on the right-hand side. It has fractions. We don't usually have fractions in Cartesian form. No fractions, no decimals. So to get rid of fractions, you might remember, we take the whole expression, times it all by 4, and we'll end up with 4 times 1/4 is just x, 4 times y is 4y, and 4 times 2 is 8. And the reason I chose number 4 here is this is my lowest common denominator. Okay, and then we have Cartesian form. Now, that's great if we have mx plus b, but as you know, most of the time we don't have mx plus b, we have a vector form or a parametric form. So we need a way that's going to work in R2 and R3 from vector to Cartesian. Okay, so yes, that connection exists, but we're going to use vectors to just work for us. So here's the big idea for today. In this diagram below, we have some line L. Okay, it's a line, it's an R2, it has a vector equation. We can figure out what that is if we wanted to. R equals some point, xy, plus some direction vector, xy. Okay. If we draw a perpendicular line to this, the blue one, this perpendicular line, which we call a normal vector, okay, makes a right angle with the line that we want. Okay. The perpendicular line has a direction of itself. The direction we call the normal vector, made up of a comma b. So two values are your x and your y parts. If we want to find the direction of m, the vector of this one, n and m have some relationship because they're perpendicular. Their dot products have to be 0. Well, the nice thing with these two vectors is that a and b actually form the coefficients. A and b form the coefficients of the Cartesian vector of line L. Okay, so if we can, as I said, if we can find a perpendicular vector, which we know there's a shortcut for doing that, then we actually have the Cartesian coordinates. And all we have to do is solve for C using some known point. So if we go back to the first one for just a second, okay, the direction of M in the very first one here, M was 4, 1. So it's perpendicular, which we're going to call the normal vector. Remember we said our shortcut was switch the order and change one of your values. Let's change the sign. Well, if you notice, that's what we get here. And so I could start off by, as soon as I see what my M is, I know the N, and I could write it in as, sorry, not that, 1x minus 4y plus some value comes out to 0. To get the value, I take a point that I know from my line. We knew 0, 2, so I can put 0 in, I can put 2 in, I can solve for C. 1 times 0 is 0, so I get minus 8. In other words, I get C is 8, which we got. Okay, so it's a way of finding your Cartesian equation very quickly by knowing something about the original vector. And the fact they have a relationship between a direction and a normal. And that's our previous example. So let's take a look at the next one. Okay, we already did this previous example. We'll try this one. Find the Cartesian form of this. So what do we need to know to find the Cartesian form? We need to know M. M is -5 and 2, the direction vector of your, the direction of your vector. Your N, your normal, is its perpendicular. So 2, 5. We swapped one of our values. These form the coefficients. So 2x plus 5y plus c has to come out to 0. And we have to use a known point. Now the point that we know for sure from this form is 3, 0. So if we fill that in, 2 times 3, 5 times 0, c, we'll get 6 plus c is 0, c is -6. Therefore, our Cartesian vector or scalar vector for this, Cartesian equation or scalar equation for this vector is 2x plus 5y minus 6 is 0. And then we got 3 forms. Okay, so you can try one. I want to find the Cartesian equation aligned through these 2 points. See what you can do. Okay, so we got 2 points, your choice which one you want to use, but we need a direction. So M is to be this one. AB will be 1 minus 4 is -3. 3 minus 2 is 1. So we know our Cartesian has the opposite, the perpendicular. So 1, 3. We got x plus 3y plus c makes 0. Your choice which point you want to use. I'm going to use b because it's a small number. So 1, 3 times 3. So I'm going to get 10 on this side. So c is -10. And my Cartesian would be x plus 3y minus 10, 0. Okay, hopefully you got that one. Take a look at the next one. Determine the vector, parametric, and scalar forms for the equation x equals 3. So what is x equals 3? Well, that's a vertical line, right? It goes up through 3. If I want to find the vector equations for that, well, that's something we know how to do. My vector equation would be go through a point that you know. What point do we know? Well, we know for sure it has to go through the point 3, 0, or 3, 1, 3, 2, 3, 3, 3, 4, any of these points, right? These are all points on that line. So you have an infinite number of choices. The easiest one to pick would be 3, 0 plus t. And what direction is this going? Well, my x direction is never changing. It's 0. My y direction, I can pick any number I want to. I can go up by 1s, I can go up by 2s, I can go up by 3s. 1s would be the easiest. Okay, and if that doesn't quite make sense, think about the next point would be 3, 1, right? So if I went from 3, 0 to 3, 1, your your direction is 0, 1. It's kind of a special case because it's a vertical line. Same thing is true with horizontal lines. Okay, parametric, x equals 3, which should make sense no matter what. X is 3, and y would equal 0 plus t, or in other words, just t. You can pick any number you want to, and you can get the new thing for y. So scalar forms. How are we going to do the scalar version of this? Well, m was 0, 1. So we got to find n. M was 0, 1. So n, that's perpendicular. If we swap them, we end up with 1, 0. Now, we have to change one of our signs, right? So I changed the sign to 0. You can't tell that because 1, negative 0 means the same thing as this, but I did change the signs. You could also change negative 1 if you wanted to, but there's no reason you need to. So my coefficients are x plus 0y plus c equals 0. Well, 0y is just 0, so we don't usually show that. So we have x plus c is 0. And what do I know for a point? Well, I know 3, 0 is a point. 3 goes in for x, 0 goes in for y, but there is no y, so you don't really worry about that. What do I get for x? I get x is negative, sorry, not x, it should be c is negative 3. In the wrong spot there. Fix that. So, sorry, 3 plus c is 0. So c is negative 3. So our equation, x minus 3 is 0. Which really, if you stop and think about it, is just a rearrangement of this, right? X minus 3 is 0. So is it worth it to go through all that work to do that? I'd say no. As soon as you see you have a horizontal or a vertical equation, the only thing to do to put in standard form is to bring the one number over to the other side. Okay, so vertical, horizontal lines, things we just talked about. Okay, since the slope of the vertical line is undefined, the direction has a horizontal component of 0. And like in the previous one, we could choose any number we wanted for our direction vector, right? We got to pick whatever I wanted here. I said you could use 0, 1, 0, 2, 0, 3, 0, 4. Okay, and you can use any point on that line. The easiest point we picked was 3, 0 because we knew x was 3. Okay, that's almost like a shortcut. For vertical lines, sorry, horizontal lines, you can do the exact same thing, except for this time your x component is going to be whatever value you choose. Okay, just no ideas here. Parallel lines, any lines that have the same direction vector, well, their scalar multiples show that they're parallel lines. So if I saw something that was r has a point of 0, 1 plus t times 2, 4, then I saw another one that had 0, 7 plus t 4, 8, I would know those two are parallel lines because these two things are scalar multiples. Okay. If the direction vector is the same, their normal vectors also have to be the same. So if I were to see a scalar equation, 2x plus 4y plus some number, and I were to see another one that had, I don't know, for example, x plus 2y plus 6 is a number, I would notice that the scalar multiple is the normal part for this one, and the normal part for this one are scalar multiples, which tells me these lines are also parallel. Okay, so same normal vectors means parallel, same direction vectors means parallel, and for our future reference, we're going to call this coincident. Okay, if they have the same, c value, or sorry, scalar multiple of c value. So these two lines are parallel. A coincident one might be x plus 2y plus 5 equals 0, because two of these makes that. So same line, different version, coincident. Same normal vectors, parallel. Okay, so let's take a look at these two things. Show that they're parallel and non-coincident. So parallel means looking at their scalar multiples. I want to look at their normal vectors. So normal vector number 1 is 2, 6. Normal vector number 2 is negative 8, negative 24. And if I take a look at that, I can say that negative 4 times n1 comes out to n2. Since those are scalar multiples, they must be parallel. Okay. How do I show they're non-coincident? Well, negative 9 times negative 4 does not equal 30. Therefore, they're non-coincident. Okay. The entire equation has to be a multiple of the other one to be coincident. Last idea, I want to sometimes look at the angles between our lines. We've talked about R2, R3, and how these vectors move apart from each other. The easiest way to figure out the angle that they meet at each other is figure out the angles between either the direction vectors or the normal vectors. Either way, you can get the same angle. So we're going to go back to dot product for a minute here. Our dot product rule was cos theta equals A dot B over A times B. If I use that formula and use my directions, I can very quickly figure out the angle that the two lines meet at. Okay, and remember, we always use the acute angle. So if you get an answer of 150 degrees, we would take the idea of 30 degrees. And so I have two lines here. I want to find the angle between them. So I could take direction vector 1 would be negative 2 and 1, and direction vector 2 would be 3 and negative 5. Now if I want to find the angles between those two things, my cos, back to dot product, just quick reminders, multiply and then add, okay, over the root of negative 2 squared plus 1 squared and 3 squared plus negative 5 squared will give us negative 11 over root 5 and 34. And what is the inverse of all that? So all in our calculator, and that comes out to 147.5 degrees. So in this situation, obviously we have two lines, vector A and vector B. They're crossing at the 147, which is fine, but remember we always want to talk about this acute angle here. So the angle between them would be 180 minus 147.5, or in other words, 32.5 degrees. And that's Cartesian equations and angles.